Okay, hello everybody. So this video is the first topic we're going to look at as we get into the second part of the course, which is about something called integration. And we'll get there eventually, but for right now, I just want to talk about one specific thing that it's not obvious why we care about it, but I'm going to explain why. And that is the area underneath a rate function. And by underneath, I mean in between the function and the x-axis. So if I have a rate function that looks like this, the area we're talking about would be this part under here and this part under here. So that when we talk about the area under a curve, it means between the curve and the x-axis. Technically, this area over here is not under the curve. It's kind of above it, but we mean between the curve and the x-axis. Okay, so what do I mean by a rate function? So a rate function is a function that describes the rate of change of some quantity. So we've seen a lot of examples of this so far. Velocity is the rate function of position. Acceleration is the rate function of velocity. You can think of others. If I had some function that told me the water level in a lake, then the rate function would be telling me at a given time how quickly was that water level changing. Derivatives are rate functions. We actually have gotten pretty good. If you give me a function, I can find its rate function by taking the derivative. Derivatives tell us the rate of change of the original function. So what we're going to start looking at is there some way to go the other way? So we know if we're given a function that tells us the level of some quantity, we're very good at finding the rate function. Now we're going to start asking the question, well, if I know the rate function, can I reconstruct or know things about the original function? So the example we're going to work through in this presentation, we're going to be looking at velocity, and if we know the velocity of a particle, what can we figure out about the position function? So let's take a look at that. Okay. So we're going to start with a pretty simple velocity function. It's going to be a particle. It starts off going 4 meters per second, and then once it gets to 6 seconds, it suddenly starts moving backwards to the left at -2 meters per second. And then after a couple seconds, that switches back to 2 meters per second. So the question is, can we figure out how far this particle traveled during this time? So can we figure out its change in position in between t equals 0 and t equals 16? And I think the answer is yes. Right? So what I'm going to do is I'm going to split this function up into 3 different segments. Okay, so during segment 1, the particle was traveling 4 meters per second, and it traveled at that rate for 6 seconds. So if you're going 4 meters per second and you travel for 6 seconds, you have traveled 24 meters. And that is the area under this, under the function up to this point. So then, if I am traveling -2 meters per second for 2 seconds, I have traveled -4 meters during that whole time. That's the area of this square. And then in the last segment, I am traveling for 8 seconds, and I am traveling at 2 meters per second. I have traveled 16 meters per second. So 2 meters per second for 8 seconds, that's 16, right? So if I want to find out how far the particle traveled from its initial position, I just add up how far it traveled in each of these time periods. So I have 24 minus 4. I move to the left by 4 meters. Then I move to the right by 16 more meters. So you get 20 plus 16, which is 36 meters. So good. Notice that I don't know at this point that at t equals 16 that the particle is actually at position 36. The only thing we have found here is how far the particle moved from its initial position in between t equals 0 and t equals 36, or t equals 16, sorry. So we know that during this time period, the particle moved to the right by 36 meters. In order to know where the particle is, at this time, we would need to know where was the particle at t equals 0. So we know that the particle's position at t equals 16 is the initial position plus 36. So we ended up 36 meters to the right of whatever the initial position was. So if the particle started at position 0, then yes, it is 36. It is at position 36. But from this information, since we're only given the rate that it was moving, we don't know where the particle was at t equals 0. So we don't know for sure where the particle is at t equals 16, but we know that in between t equals 0 and t equals 16, the particle moved in total 36 meters to the right during that time. That's going to be important later on. Okay, on the next slide we have a slightly more complicated velocity function. So here, the velocity of a particle is given by the function 3t. So let's see how far the particle has traveled after 4 seconds and then after 8 seconds. So at 4 seconds, I think these little squares are each 2. Okay, so this is t equals 2. So it's the same principle as before. The only difference in this one is that your velocity isn't constant over a period of time, but the area underneath the velocity curve still tells you how far the particle traveled in between time equals 0 and time equals 2. So if we want to find out how far the particle traveled, we just need to find the area of this triangle. So we know that this height, when we plug in 2 into 3t, we get that the height is 6. Oh, it's because I'm on 4. Eesh. So this is actually t equals 4. We'll do t equals 4 first. So this height is 12. That makes more sense. So the area of this triangle, distance traveled at t equals 4 is 1/2 times 4. The base of this triangle is 4. The height is 12. And we get 32. All right. Okay, so the total distance traveled after 4 seconds is 32 meters. Let's figure out how far the particle has traveled after 8 seconds. So this is t equals 8. To find the total distance traveled, we need to find the area of this triangle. Okay, so distance traveled Okay, so still want to find the area of this triangle. The base is 8. The height is 3 times 8, which is going to be 24. Okay. 8 times 12, I want to say, is 96. So the particle has traveled 96 meters since then. So this is nice. The area under this curve is always a triangle, and we have a formula for how to find the area of a triangle. So let's go ahead and see if we can come up with a general equation for how far the particles traveled. So instead of finding how far the particles traveled at a specific time, I'm just going to pick some random time here. I'm going to call it t. So the distance the particle has traveled in between 0 and t is the area of this triangle. So let's see if we can write an equation in general terms for this. So the area of this triangle is 1/2. The base is just t, right? So that's the base of this. And then the height, whatever the value of t is, the height is 3 times t. So the height is 3t. So if I go ahead and multiply this together, I get 3/2 t squared. So the total distance traveled at any given time, t, is 3/2 t squared. So this is actually, what we've done is we have found a position function. Because here, when we plug in time, we get how far, so it's not actually the position function, it's how far the particle has traveled since t equals 0. So almost a position function, right? In order to turn this into a position function, as I was saying earlier, we need to know what the particle's initial position was. So we know that the actual position function is going to be 3/2 t squared plus the initial position. Whoa. That's fun. So if I were given some extra information in the problem, like the particle started at position 0, or at t equals 5, the particle was at 25, I could figure out with that additional information what the initial position was. But without that information, this is as close as we can get to a position function. But, you know, that's pretty good. And you notice that if you take the derivative of this position function, you actually get the velocity function that we were given. So p prime is 2 times 3/2 times t. These cancel, and you actually get that the velocity function is 3t, which is what we started with. So that's kind of cool. Okay, so just to wrap this up, we were able to do these problems because we actually know easy little geometry formulas for the shapes that were created under the curve. So the first one, the shapes of rectangles. The one we just did, the area under the curve was always a triangle. Other linear functions, you might have a trapezoid underneath the curve. Obviously, not every function has, you know, a nice shape underneath it that we know a formula for. So in this graph here, you see this is just a parabola. If I wanted to find the area, underneath the curve at 5, I don't really know a formula for this shape, right? So what we're going to be looking at coming up are different techniques people have used to approximate or estimate the area underneath something like a parabola or any curved line. Because theoretically, that area means is still the same. You know, if we wanted to find, you know, if this was the velocity function for a particle and we wanted to find how far it's traveled, we would still want to find the area under the curve. And so figuring out ways to estimate that area, or eventually what we will do is figure out ways to find it exactly, is still desirable, because this is a process that, just like we saw in the last example, will allow us to reconstruct an original function when we're given a derivative. So just like in the example we just did, where we were able to start with a velocity function and develop a position function, we want to be able to do that for any kind of derivative, not just linear ones. So, you know, if the derivative is a parabola, we want to be able to find the position function. If velocity is, you know, a trig function, I want to be able to find the position function, et cetera, et cetera. So that's what we're going to be working on. Fun times. Thanks for listening.